Okay. So as Brian said, my name is Rich Graham. I'm from Mellanox. And what I'm going to talk about today are things that we're doing at Mellanox looking forward to extreme scale computing. So first of all, in terms of some direction, some guidance for in terms of how we progress in terms of features for aimed at HPC, I have a listing here of items that were extracted from several Exascale reports, talking about some of the challenges that face us. I guess now it's not that far out, maybe 5 years away by now. In terms of things that architectural things that need to be addressed to be able to scale to very large systems. And just to give you an idea here, in terms of the items I'm going to talk about, I've highlighted in green the ones that I'll address explicitly in this talk. So obviously, there's a need. There's the expectation of being very large functional unit counts. That means whether it's a CPU, whether it's a GPU with thousands of small compute engines or anything else, whatever it is, the direction is going towards large quantities, and therefore the need to be able to scale well to support these large quantities is big. On top of that, you also have single sources of a single host generating a lot of data. The functional count of order 500, I'm not sure what it means today with all the different architectures that are being looked at. In any case, you need to, from a communication perspective, you really need to have an architecture that scales well to be able to support a lot of a single point either generating or receiving large amounts of data. Independent progress is very important. You want to be able to not have to use CPU resources to make sure communication progresses at the rate it should, and that the system as a whole performs well. And then in terms of network optimizations, as your blobs of hosts get larger and larger, it's more of a challenge to keep the network itself utilized well, and that's addressed by technologies like adaptive routing. So to give you a bit of an idea of where we are today, this is really one of the things that gives credibility for us to be able to talk about longer term plans. Today we're at the 100 gigabit per second technology. And a few of the characteristics of this current technology or EDR technology. So it's the host channel adapter that is part of this family is the ConnectX-4. It has a peak bandwidth of around 100 gigabits per second. I'll show you in a while. Measured bandwidths are very close to peak. Latency, zero byte or zero user payload latency is actually close to 0.6 microseconds. Message rates, high message rates on the order of 150 million messages per second. That's very important for supporting a lot of sources of data. And it can run. It's backward compatible with previous generations and can run at lower speeds if there's a need for that. From a switch perspective, the switch is an InfiniBand switch, InfiniBand only switch IB. It's a 36 port device running bidirectional 100 gigabit per second each direction. Latency is under 90 nanoseconds per direction. So this is industry leading and less than half of what the previous generation latency was. And it really does able to drive full bisection bandwidth through that device. From a cables perspective, we have support for copper as well as two types of optical cable. VCSEL-based and silicon photonics. The copper, of course, means copper can run up to several meters in terms of, and what that means is you can use copper technology, which is cheaper and doesn't use electricity to drive communication within a cabinet and even between neighboring cabinets, depending on your design. A few more details on the switch. So as I mentioned before, some of the one of the important areas to address as you scale out is the ability to utilize your network effectively, and so there's additional support added for adaptive routing in this switch, and I will describe that later on. In addition to that, we've also added support for InfiniBand routing, an InfiniBand router, and what that means is that you can with this technology now you can route between subnets using RDMA with essentially no penalty. There's a small conversion cost. It's on the order of 10 nanoseconds or so to go between subnets, and also the number of routers that you can have in a subnet in your network is not limited. That is, if you want to, in principle, even you could have a router at every switch, and what that means, and so that's important. So this is important for two reasons. One, you now have administrative isolation between your compute storage and for example your file system. So you can administer them independently, and from an administrative perspective, they're independent entities and don't influence each other to the extent that, of course, if you need the file system and it's down, you can't access it. But otherwise, they're independent, as well as a way to actually extend the size of the system beyond just a single subnet. So it's a way to increase system size. Yes.
Is it integrated already with the switch, or this is
yes.
like additional?
No, it's in the switch hardware. Yeah. In addition to that, some of the things to point out about the host channel adapter, aside from the base speed and feed, some of the other technologies that have been added here is support for open power for CAPI technology. That is for cache coherency with a CPU. Also, and some enhancements to the core direct technology, which is used to offload collective operations. So there's support for doing data reductions on vectors now. So you can send in 2 vectors and output 1 vector on the network and maintain network bandwidth. Enhancements to GPU. GPU Direct continues to be supported. Dynamically connected transport, which I will talk about soon, which is a scalable transport. There are enhancements to it made, as well as support for several of the Ethernet offloads. Just some actual data from this system. I have latencies here, short message latencies for MPI, latencies using the OSU bandwidth test for EDR and FDR, that is Connect IB, without a switch. You can see that from a latency perspective, these are similar. The EDR is slightly higher, a slightly lower latency. When the switch gets involved here, because the switch latency is considerably lower than switch IB than Connect X2, you can see MPI latencies here benefit from that. So you get nice, good latencies there. Bidirectional bandwidth. Again, these are at the low size. These are unidirectional and bidirectional bandwidth up to 1,024 bytes. Again, FDR and EDR at this size are similar in performance, but once you get to larger data sizes, of course, bandwidths for both unidirectional and bidirectional bandwidths for EDR are close to twice as not quite twice, but close to twice as much as FDR is, and so you see we're able to get very close to theoretical peak with the bidirectional bandwidth here, and as well as unidirectional bandwidth. We're also getting extremely good bandwidth. So this is the blue here is EDR single directional. The red here is FDR bidirectional bandwidth. So overall, the performance, bandwidth performance is very good, and you'll see later on in the applications this has very good, very positive impact on application performance depending on characteristics. A bit about collective communication. So here's barrier characteristics for Connect X4, which is the EDR device, and Connect IB, which is the FDR device. Barriers at this small scale are similar. I'm sorry, the performance is similar, and because latency characteristics of these two devices for point-to-point communication are similar. We go to collective operations that start to move more data around, like even an 8-byte all reduce. We can see that the benefits of EDR starting to, even at this small data size, starting to show up. This is, as I said, 32 hosts. If I remember correctly, this is a Haswell processor, so it's probably 28 processes per host. So we're starting to see some performance benefits here. And as the size of the data increases, of course, the benefits become larger. And this is reduction, again, similar type of behavior. And so it really depends on your application, the mix of communication patterns is one of the factors that contributes to changes in application performance, not the only one. So let's start talking about scalability here. As I alluded to earlier, a new transport has been introduced into InfiniBand, actually starting with Connect IB. It's called Dynamically Connected Transport, or DC. And DC, the intent of DC is to start addressing issues of scalability of the network at extreme scale. So a few characteristics about dynamically connected transport. So it's a connection-based transport, but the connections are managed by hardware, and their duration is long enough as long enough as is required to deliver the data. And I'll explain a bit later what that actually means. Another thing, an important aspect of this is it's similar. It has a similar characteristic to unreliable datagrams for those of you that are familiar with InfiniBand, in the sense that you can have a single one initiator sending data to multiple destinations. So that gives you the characteristic of being able to keep a small number of initiators independent of the size of the system and scale up well. It also has a characteristic of providing reliable transport. So just like RC, it provides a reliable transport. Now a few more details here. To support a reliable transport, you need to maintain enough state to get an acknowledgement, to send the data, and then confirm that the data has been received. The underlying transport is actually exactly the same underlying transport as is used by RC. And so what that means is, for example, if you think about the most latency sensitive traffic that you have, your small data transfers, say your 8-byte MPI data transfers, which you or even SHMEM or whatever you use, those you need to maintain state for a round trip on a communication. That means you need to be able to send the data to your remote sites on the order of a microsecond, really almost independent of system size. It's not totally independent, but almost, and then get the acknowledgement back. The other characteristic of any device is that the device can only drive. There's an upper limit in terms of how much traffic a single device can drive. So if you think of our Connect X4 device, where I just told you it can drive 150 messages per microsecond, which is a very good rate, industry-leading rate, as a matter of fact. So it's very, very good rate. What it means is to be able to keep the network at capacity in terms of service. You need to be able to cover 2 microseconds of round-trip traffic. With a message rate of 150 million seconds, 150 million messages per second, that means, or 150 messages per microsecond, all you have to drive, 300 initiators will drive, is the limit on how many initiators you need to drive the system to fully utilize the system, independent of the system size. And so what this does is this really does provide a scalable transport, a reliable transport that allows you to do RDMA operations, atomic operations, and the like that can scale to extremely large scale, and really does address the issue of scalability of transport. The additional advantage that it has is all communication, all connection setup is handled by hardware on demand. No need for any heuristics or anything like that in software or other places. And so resource utilization here is very effective, and it's actually very simple to use. So just a picture here in terms of a single initiator to multiple targets. And so if you think about some of the communication patterns that people use, think for example about the all-to-all communication pattern that an application may use to send data. If you're using RC, reliably connected transport, you'll need connection from one host to everyone else, from process to process. And so you end up requiring very many connections, and the number of connections grows as the system, or actually the job size grows. And so with dynamically connected transport, you can have the same communication pattern that will just reflect the underlying network utilization. So typically in all-to-all optimizations, no one sends all the data at once. You try and coordinate traffic to reduce effects to reduce network congestion issues, and this gives you a very, very good way to do this with really the pattern of communication changing over time. A bit of performance data here. This is performance data that was collected a couple months ago, looking at how on an all-to-all system, I believe this was for 128 nodes. What is the latency of an all-to-all operation using dynamically connected transport versus UD transport? So this is a ratio. Above 1 means that dynamically connected transport is running more efficiently than UD, than the unreliable datagrams. You can see here that for the data plotted here, DC is showing good performance. So we show UD here because UD today is the transport that most people, the InfiniBand transport that most communication libraries developers use to address issues of scale. So a few other things in terms of network scalability. So from a topology perspective, we were really agnostic to, the hardware is agnostic to the sort of topology it supports. The hardware is capable of supporting basically any topology you want. You just have to have the software to go with it to set up your network tables and the like. And so we've put a lot of effort into supporting fat tree. Most of the systems that we deal with are fat trees, to some flavor of fat tree. There are systems out there that are mesh based, but we also do have support for Dragonfly. Dragonfly Plus is the name we gave it, topology, and the plus is indicating really the indication that within each of your local pools, the topology that's used here is a two-level fat tree topology. Well, I mentioned already the fact that we've added support for routers, and being able to route traffic between subnets using RDMA, not needing any sort of translation in the middle, any sort of translation node or anything like that. Also enabling you to do, if you wanted to, atomics after between subnets and the like. So really extending the range of RDMA capabilities, and we also have added support for, as I mentioned, have added enhancements actually to the support for adaptive routing. So adaptive routing has actually been supported, or is supported in our switches, starting actually with our EDR switches. Switch X2 supports adaptive routing, and this is actually in production release these days. The goal of adaptive routing is to improve network utilization, to deal with, as you scale up, if issues of congestion tend to come in, and so to deal with increasing the effectiveness of the network with scale, as well as to help with. This also helps with network resilience. That is, if you yes.
So. Get to next level detail of what is a congestion, because there could be like something that is software detected that would take something that persists for a while, or it could be something that is very sporadic. How is this? It's like a hardware.
Yeah, this is hardware that deals with this. This is hardware that detects basically the state of the network at the hardware level.
Packet by packet.
Oh, absolutely. Yeah, everything at that level is monitored very, very carefully. Yes.
There's some experiments with software-based controls, and that you were to adjust it. With latency, that the situation is already completely different.
That's right. That's right. So I'll talk about a feature that this is what's coming up here. We have a feature to deal specifically with exactly what you're talking about, the adaptive routing notification, which is intended. So this is not software that's handled at the endpoints. This is really at the switch that handles live traffic as is. And let me describe it a bit more, and I think I'll answer some of your questions in the subsequent slides. And if I don't, just ask again, bring it up again. And as I just indicated, a new feature has been added to the EDR switch IB, and that's called adaptive routing notification. And the intent of adaptive routing notification is to accelerate convergence of adaptive routing, give it some global input into routing decisions, more than just local switch input. And the effect here, the estimate here is that for long data flows, or for long data sizes, convergence of adaptive routing is on the order of 10 microseconds or so. So quick enough to influence actual, if your traffic, either if your patterns are persistent, of course that's easy to deal with, but for larger data, data that lasts more than a few tenths of more than on the order of 10 microseconds or so, be able to actually impact the traffic as it's going on and improve its performance. So a few things about the hardware. If you're supporting when you support adaptive routing, doesn't mean that everything has to be adaptively routed. You can continue and have some traffic that's statically routed, but other traffic but have other traffic that's routed, and the granularity at which you can do this adaptive routing has several different granularities. As I said, one of them, I think this is actually addressed. Yeah, one of them is never. If you have statically adaptive routing, you'll never adaptively route those. You can have traffic classes that are time bound. That is, you'll change the entire flow over a period of time, not with each packet. So for those sort of traffic that out of order may for some reason give difficulty at the application level or something like that, you can make sure that happens less by using this sort of adaptive routing. But you also have a packet by packet decision as to route or not. And all those are configurable. All those are simultaneously actually supported on the switch. You can have all three types of routing happening simultaneously. So to explain a bit more about the feature that I called adaptive routing notification, as I said, the intent of this technology is to accelerate convergence of the adaptive routing, so that it has impact, so it actually has a better chance to impact ongoing communication, and not like you talked about, adapt to what happened X amount of time ago that's no longer relevant, but to make it relevant to current traffic. And the intent here, and part of what happens here is this mechanism is non-local. You'll see here from the figure. It actually brings into account takes into account the total flow in making a decision whether or not to route or not, or whether to reroute or not. So the switch samples the flow, and when it detects congestion, what it does is after you exceed a certain threshold, it determines that it needs to adaptively route, and it tends to favor rerouting large flows, because those are flows you have more chance of impacting, rather than taking your single packet, for example, flow that by the time you've received the packet, it's too late to do anything about it, unless you have unless you can't proceed with that route at all because of failure. So when it detects that, it sends an adaptive routing notification to the source of the data, that is the switch beforehand, and that switch decides what to do with that adaptive routing notification. In this case, it's not the source of the data, so it cannot impact the flow of data that came to it, and so it also forwards that message to the switch that it received the data from. Where in this case happened to be the source of the data, and so the route can be changed at the source of the data, and the congestion avoided altogether. So that's basically the intent of adaptive routing. So I have some performance data here. This for the Be Effective benchmark. The Be Effective benchmark basically uses a shift type of communication pattern. It's not exactly a shift, but it's very close to it. For those of you that are familiar with shift, what it means is you basically actually it uses two shift patterns. What it does, it arranges processes in what it calls a ring, where within the ring every process communicates, receives data from one neighbor and sends data to another neighbor. They're not coupled; they happen simultaneously. There's no token chain moving around a ring or something like that. The other thing that's characteristic about this application is that you don't get into situations of end-to-one type of sending. That is, you have distinct pairs that send data between each other. And so at least from a theoretical perspective, if you're in a class network, you have a chance of having zero conflicts in routes. But the reality is that you do, because of the nature of this test, you do end up running into congestion, because there's some scrambling that's done in terms of which pairs actually interact with each other. And I have the performance data here shown for of Be Effective. This is after adaptive routing is enabled for FDR devices. This number is a simulation, so we see for FDR that we get close to, for this particular benchmark, this is measuring the large data portion of the benchmark. For those of you that are familiar with it, this is LMAX. So it's getting pretty close to full network bandwidth. Without adaptive routing on, the bandwidth starts to tail off fairly quickly. It doesn't get to half at 64 yet, but it tails off fairly quickly. We have comparable data points for the same benchmark run on Cray Aries. over out to a larger number of nodes, and we see that the performance of FDR here is better than that of Cray Aries. And very recently we obtained some EDR results for this benchmark. And we see that, as expected, the EDR performance is much better than that of FDR. This at this stage is without adaptive routing notification. That hasn't been turned on yet. Okay, now we'll switch gears and talk about a bit about network offload briefly. Another type of network offload, I should say. All our devices are offloaded to the card, and everything is done on the card. So, several years ago, we added a capability that we called Core Direct, and it was a technology that was introduced to allow to coordinate between different flows in the network. And it was targeted explicitly at providing support for collective communication. So 2 reasons to provide support for collective communication. One, it's very important in many scientific applications. For many scientific applications, the performance of collective operations determines both overall scalability and performance of the application. There are other parts, of course, that are important, but this has a big impact on application scalability and performance. The second thing is this particular type of flow suffers from what's called system noise. That is, anytime the system, if you're trying to progress the collective communication, and the system has to provide some service, it gets its time sliced to provide its service, it's slowing down the progression of this collective communication. And therefore delaying the progress of the entire collective operation. And for those of you that are familiar, there was a famous paper from around 2003. I think it was Fabrizio Petrini was the lead author of it, talking about the Q machine at Los Alamos, where they looked at these sort of things. And I think the system at that time was on the order of 6,000 nodes. I forget the exact size, but overall impact of system noise on application performance is about a factor of 2. So this is a big deal on systems. So if you can avoid those effects altogether, that's a good characteristic. So the reason this is an issue is because in collective operations you have dependencies between flows. So I have a picture here of something that could be a barrier, it could be an all reduce, or something like that. But the point here is, for example, the circles here represent the initiation of some sort of network activity, some sort of send in this case, and what means this second send, from process 0 to process 2 can't happen until data was received from process 1. And in this case also from process 2. And so this dependency between processes is what makes this a scalability challenge, and 2, what makes it susceptible to system noise. And so if you have a mechanism where you offload all the management of this collective communication to the network, when the system wakes up to do its activity, it doesn't influence it. And furthermore, this is designed very explicitly to support non-blocking collectives. So you'll be able to set up your collective communication, fire it, go off and do whatever computation needs to be done, and then come back and see, is my data ready? Can I use it now and progress? So briefly, the key idea here is that there were some Core Direct basically introduces three new network operations that involve synchronization. They allow you to wait for a completion of an event happening at another queue. They also allow you to enable operations waiting in another queue to begin. And so these are enough primitives that let you build collective communication capabilities and give it to the network and let the network go on its own. It also has the ability to let you calculate. So you can do your reductions for your MPI or SHMEM reductions on the network without having to involve the CPU in the process. And so when I say that in ConnectX-4 we've added support for vector reductions, that means you can pass in a vector of data, or two vectors of data or more, reduce the data and send it out as part of one of these offloaded patterns. And so, as you would expect, because the hardware was designed to do this, when you use core direct capabilities, you get a lot of CPU cycles available for computation as the communication is progressing. And so if you have an application that takes advantage of these sort of things, you've given yourself some good ingredients for scalability. So this happens to be the percent of overlap available, or percent of CPU available for computation in an all-to-all operation as a function of message size. This is the core direct offloaded capability, and this is an implementation of all-to-all that uses the core direct capability. This is an implementation of all-to-all within the same infrastructure that uses the CPU to progress communication. And so you see a big advantage to offloading things to the network, offloading this collective communication to the network. Another technology that's been added to address offloading capabilities is adding support for non-contiguous data transfers. Today in many applications, if they need to send or receive non-contiguous data, what happens at the communication library, at your MPI library, you basically create a temporary buffer, copy the data into the buffer, send it, receive it on the other side, and unpack it. You can do a bit better than that if you can take advantage of some of the data packing capabilities that are defined prior to this in the InfiniBand standard. You can send things with you can send data with what's called an IOVEC. It's basically a list of pointers and lengths. So an irregular structure, it's limited in size. You can do the same thing on the receive side. You can receive into something that's described by an IOVEC, but you can't use RDMA going from non-contiguous to non-contiguous. And before this capability was added, which we call UMR, for user-level memory registration, you did not have the ability to go from non-contiguous memory to non-contiguous memory. What's been added in UMR is there's been added a definition for memory keys that describe regions that are non-contiguous. So your description of the operation happens in an entity that's recognizable by InfiniBand, and InfiniBand hardware can do something specific with it. What's added more than that, it's been added also a very compact description of data that's laid out in a regular structure. So if the red and the green here represent regions of memory, sections of regions of memory, where the contiguous portion goes from left to right, and so we have items that are separated here by looks like six units of displacement, whatever those displacements are. And so you have a very, very compact way to describe this, which is very good for the hardware. And more than that, you can actually describe a memory region that interleaves these. So you can take two non-contiguous regions like this and interleave them, and on the network have something that goes out like this. The data that goes out on the network is actually like this, and this is all handled by hardware. No need to pack at the software level or anything like that. And so really, this frees the CPU from needing to spend time on packing data and unpacking data, and it adds a capability to do RDMA operations from non-contiguous user space to contiguous user space on the other side. So again, the intent here is to free up the CPU to continue progressing computation as the network to free up the CPU for computation as the network is sending the data along. So a small amount of data here on the performance of UMR. we're actually early on in starting to use it in a variety of ways. I have here plotted as a function of the size of the data chunk that I'm sending. So 32 bytes in this particular case means you have 32 bytes of data you're going to send, 32 bytes of data you're going to skip, 32 bytes of data you're going to send, 32 bytes of data you're going to skip. So 3 different data sizes used. Total length of the data size that's being sent. And this particular send happens to be sending data from non-contiguous data from a non-contiguous region to a contiguous region. That was just the way the test was. This particular test was written. And we see that as the size of the data. So first of all, I should say that a number greater than 1 means that if you pack number greater than 1 means if you avoid the packing, it's better to the latency of the packing is higher. Packing into a contiguous buffer and sending is greater than 1 is less efficient than just sending directly from user space. And so we see as the size of the data increases, it becomes more and more effective to use this capability. This is from an absolute performance perspective. If absolute performance is not the most important thing, so if you have enough time if you're also an important criteria for you is being able to fire and forget from a communication perspective, even if the performance is maybe the absolute performance may not be as good, you have the ability to hide that in the background if your application can do that. And so I also provide benefits to the application in that perspective. So I said I would talk a bit about application performance, and specifically with respect to EDR. So I have here some performance data for several engineering codes, comparing the performance of these applications using InfiniBand FDR to InfiniBand EDR. So really the only change between these two is the network. And we can see that, for example, for this particular application, we see a total application performance. This is total application performance of increase of 40%. For RadioSys here, we see a 25% performance improvement at 16 nodes. This is an LS Dyna test code. We see around 15%. A lot of times we see performance improvements on the order of 10%. Of course, this depends very much on the characteristics of the application. For WARF, yes?
Go back please to this one slide.
Yes.
Yeah, so here, did you have any chance to go above 24 nodes, actually? It's a higher number of nodes. And the impact, is that different? Did it continue to increase, or you had some drops? Or?
So I didn't generate this data, so I don't know. My guess is it tends to. I don't know anything about the characteristic of this application, so I'm not going to guess as to what it did, because I don't know what sort of communication patterns. My guess is it was probably run at 24 because that's what was suitable for the test case, not for other reasons. I just don't. I didn't run this. These are just So I don't know how to. Yeah. And this is for WARF. WARF is a widely used weather forecasting application. We see a 28% improvement on overall application performance. So there, actually, I did look at the traces because I'm personally interested in WARF. Their communication really is dominated by very large messages. So going to larger number of processes, I would expect would continue to improve things even considerably. And here's some data for GROMACS. Actually, also comparing the performance data for two different types of FDR.
Right.
How much time do I have? 5 minutes. Okay. We also ran the Graph 500 benchmark and saw going from EDR to FDR about a 20% improvement in this particular benchmark. That's relevant for graph type of work. We've actually done also some application level optimization here that improved performance considerably too, but haven't published those results yet. This is at 128 nodes, so there's fairly large messages going around. You see, oh yeah, I guess this is worth mentioning here. So one of the things that we've actually started within Mellanox is a group to look at application. More than application optimization. It is how to change applications to take better advantage of network capabilities. So this group is being formed actually of people that are expert domains, not computer scientists, and so we are looking for interested collaborators to work with here. So the interest is really to understand what applications really need from the network, and also to help understand how applications currently use the network and work with the folks to try and show ways that one might be able to improve overall application performance as well as benefit yet more from what capabilities the network provides. So that's it.
Interesting.